Geometric isomerism, I told you what are geometric isomers. They are stereoisomers which have the same molecular formula, same structural formula, but different arrangement in space. And why is there different arrangement in space? Because there's limited rotation around the double bond. Yeah. In geometric isomerism, two criteria must be met. The first is you must have a carbon-carbon double bond. Yes. And the second criteria is that on each carbon, you must have two different atoms or two different groups of atoms attached. In that case, it will show cis-trans or geometric isomerism. How will you identify the cis and trans? If similar atoms are on the same side of the molecule, we call that the cis isomer. And if similar atoms are on opposite sides of the molecule, we call that the trans isomer. Cis and trans have the same molecular, same structural, different arrangement is why they have different boiling points as well. Why? Because cis isomer is more polar than the trans isomer. In the trans isomer, the dipoles, they kind of cancel out each other. So that's less polar, has induced dipole forces, therefore less boiling point compared to the cis isomer, which is more polar, has permanent dipole forces, therefore a higher boiling point. Clear? I told you that if they ask you to find the structural and stereoisomers for an alkene, you will have to include, unless they say alkenes only. If they say alkenes only, then you don't have to include the functional. And please also ensure that you include geometric isomers as well. For example, butene here shows geometric isomers. Now, butene will not be counted separately. It shows cis-trans, so they will only be counted as two isomers, not three. Clear? All right. I gave you guys some homework. I told you to do these questions right here. Dehydration of pentan-1-ol produces pent-1-ene. Sketch the diagram below. Show the orbital overlap between the two carbon atoms. Label the bonds. So this right here is pent-1-ene. So you need to show the bonds. So pent-1-ene means you must have a carbon-carbon double bond. So I'm going to show a sigma bond like this. And the pi bond can be shown as an electron cloud above and below the nucleus. Sometimes they ask you to show the electron cloud. So this right here is a pi bond. Now, these are not two pi bonds, all right? This is one pi bond formed by incomplete sideways orbital overlap to form an electron cloud above and below the nucleus. Yes? Now, oleic acid is the cis-trans isomer and allylic acid is a trans isomer of, okay, so oleic acid is a cis isomer and allylic acid is a trans isomer of this. By using the formula, draw the structural formula of allylic acid, which is what? The trans isomer. Clearly showing this stereochemistry. So let's see for the trans, what will you have? A carbon-carbon double bond right here. Yes, this carbon has a H, this carbon also has a H. For the trans isomer, what should you have? The similar atoms on opposite sides. So the H goes here, the H goes here. This one has a CH2, 7. So CH2, how many of these? 7. CO2H. And the other one also has CH2, 7 and a CH3. Clear? So right here you have shown the trans isomer, which is allylic acid, which is basically the trans isomer. Yes? Similar atoms on opposite sides. Then we have question number 4. Two types of isomerism is found in organic compounds are structural and cis-trans. Draw the displayed formulae of two structural isomers of C2H4Br2. So C2H4Br2 means C2 with 6 atoms around it. So this must be an alkane, yes, because it has 6 atoms around 2 carbons. So the configuration would, the arrangement would be CnH2n plus 2, yes. So this is an alkane, there's no double bond here. So you make C2H4Br2. You need to draw structural isomers. Can I draw this? What is this called? 1,1-dibromoethane. So this is 1,1-dibromoethane. How will we draw another structural isomer? 1,2 dibromoethane. Very good. So you put one here. This becomes 1,2 dibromoethane. Clear? Then the trans and the cis isomer of C2H2Br2. Now you have a double bond because you can see there are 4 atoms around the 2 carbons. So cis and trans. So you have double bond right here. Now, how will we show the cis? The cis will be where you have the HBr on the same sides. Yes? Clear? And what will be the trans? The trans will be when they are on opposite sides. So this becomes the cis and trans. Clear? Understood? Please don't attach both the hydrogens on the same carbon and both the Brs on the same carbon. This will not give you cis trans. Clear? Understood? Yes? Then I gave you question number 9. Draw the displayed formula of C5H10 as a branch chain hydrocarbon. Whenever they ask you to draw the displayed formula, you have to display all the bonds. You can't write the branch as a CH3, you have to display those bonds as well. So the CH3 also needs to be displayed as 3 bonds sticking out of C. Yeah. So you need to give a branched chain isomer of C5H10. So you need a chain isomer, you can't make pentene. This is C5H10, so this is CnH2n. So you can't give pentene. So give something else. Let's make a main chain of 4. Yes. And the 5th one we'll put on the 2nd carbon. This is an H. You can't write this as CH3 because you got to display all the bonds. So how will we show this? C with the H, with the H, with the H. Then you have an H here, H, and H. Clear? So this right here is what? 2-methyl but 1-ene. Yes? Clear? Pent2-ene is one straight chain hydrocarbon with the formula C5H10. Pent2-ene exhibits cis-trans isomerism. Draw and label the cis-trans. Let's draw pent2-ene. So pent2-ene would be this. Yes? Yeah. Can I write this like C double bond C with a hydrogen and a CH3 and the other one with a hydrogen and a C2H5? Can I write it like this? Yeah. So this is pent2-ene. And this isomer, you can see both the H's on the same side. This will be the cis isomer. What will be the trans? Where both the H's are on opposite sides. So this right here is the trans isomer. Clear? Understood? Any questions? Come under stereoisomers, yes? Optical and geometric, they both come under stereoisomers. Now let's see optical isomerism. So let's see optical isomers. Now, in optical isomers, because these are also what? Stereoisomers, you also have the same molecular formula, same structural formula, but different arrangement in space. So these are also, they also have the same molecular formula. They have the same structural formula, but they have different arrangement in space. Yeah. Now, for cis-trans, the criteria was you needed a carbon-carbon double bond. The criteria for optical isomerism is, so let's see, for this also 2 criteria must be met. And what are the 2 criteria? The first is you need a carbon with 4 single bonds. What do we need? a carbon with 4 single bonds, or can I say with 4 sigma bonds? Yes, because single bonds are sigma in nature. And since the carbon is making 4 single bonds, can I say the carbon is sp3 hybridized? Yes. So you need a sp3 hybridized. You need an sp3 hybridized carbon. Whereas in geometric, we needed a sp2 hybridized carbon. So you need an sp3 hybridized carbon. And you must have 4 single bonds. All 4 bonds must have different atoms or groups attached to it. So the second criteria is that all 4 atoms or groups attached to the carbon must be different. So they must be different. Yes? So 4 single bonds on a carbon and all 4 different atoms or groups. We will call such a carbon what? A chiral carbon. What do we call it? A chiral carbon. So for example, let's see, you have a carbon with 4 sigma bonds. I told you the carbon must be sp3 hybridized. So can I draw it like a tetrahedral arrangement? Because if you remember, sp3 was what? Tetrahedral in shape. So you have 1, 2, 3, and 4. If this has A, B, X, Y, do you see the carbon has 4 single bonds with 4 different groups or atoms arranged around it? Such a carbon is called what? This is called a chiral carbon. What do we call this? So such a carbon is called what? A chiral carbon. It is not a chiral carbon, it is a chiral carbon. And the molecule will be called optically active. What will we call it? Optically active, because it can show which type of isomerism? Optical isomerism. What is a chiral carbon? It is an sp3 hybridized carbon, or a carbon with 4 single bonds, you can say. So it's an sp3 hybridized carbon, or a carbon with 4 single or sigma bonds. So it's an optically, it's a sp3 hybridized carbon with 4 different atoms or groups attached to it. Yes? So you have a carbon with 4 sigma bonds or 4 single bonds with 4 different groups attached to it. We call that carbon a chiral carbon. If a compound has a chiral carbon, it can show which type of isomers? Optical isomers. So if a compound has a chiral carbon, even one chiral carbon, if it has a chiral carbon, it can show which type of isomerism? Optical isomerism. And it is called what? Optically active. Because it can show optical isomers, so we call it optically active. Now, what are optical isomers? Cis-trans, I told you, the cis was similar atoms on the same side, trans was similar atoms on opposite sides. Yes? Now, what are optical isomers? Optical isomers are mirror images of each other. So what are optical isomers? Optical isomers exist as a pair of non-superimposable mirror images of each other. So they are non-superimposable mirror images of each other. Yes, just like you have your right hand and your left hand. If I try to put my right hand on top of my left hand, you see the arrangement of the fingers is different. In one, your thumb lies to the right. In the other, your thumb lies to the left. They are non-superimposable. No matter what you do, you can never fit a right hand glove in your left hand. Yeah, just like that, because they are mirror images of each other. No, you don't have to do it like this. You put it on top of each other, they will not be superimposed. They're non-superimposable. Yes? Now, these isomers are mirror images of each other. Let's see an example. So let's see an example of how you will find out the isomers or the mirror images. Let's take an example of a carbon with 4 sigma bonds. I'm drawing it tetrahedrally because this is the conventional 3-dimensional way of showing the optical isomers. Because the carbon is what hybridized? sp3. So the shape will be tetrahedral. Bond angle 109.5. And they ask you, very often when they ask you to make the optical isomers, they tell you to show it in the conventional 3-dimensional way. So you got to show it like this. Now, let's put an H here, a Br here, a CH3 here, and an OH here. Now, if you look at this carbon, now you don't just look at the central carbon, you look at all the carbons. If there is any chiral carbon, that will show optical isomers. You have 2 carbons here. This carbon has 4 single bonds, but it has 3 hydrogens. Yes, all 4 are not different. So can this be chiral? No. This carbon has 1, 2, 3, 4 sigma bonds, and all 4 bonds are different. All 4 atoms or groups attached are different. So can this show, can this be chiral? Yes. Can this show optical isomers? Yes. So this right here is a chiral carbon, and a chiral carbon will show you how many optical isomers? 2. Yes. Now, how do you show the mirror image? Let's see. So there will be a mirror image of this guy. Okay. Now let's see the mirror image. All you have to do is, once you've made one of the isomer, which is the one that I've drawn in black, the other isomer will be a mirror image, which will be shown how you will just swap, you will just flip or switch the position of these 2. Right? All you got to do is switch the position of the OH and the Br, or the corner ones, the 2 corner atoms or groups. What will we do? This will be carbon with a H as it is. Now, the OH is to the right here. So now we will put it to the left. The CH3 comes as it is. The Br is to the left here. Now we will put it to the right. And this right here becomes your optical isomers, or the mirror images of each other. If you see right here, the molecular formula is C2H5BrO. Yes. Let's see the molecular formula here. C2H5BrO. Yes. Let's see the structural formula here. CH, Br, OH, CH3. Yes. On the carbon, you have, this is what it is. Carbon with a H, with a Br, with a OH, with a CH3. So how will we write this? CH, OH, Br, CH3. None of it will go in brackets because they are on terminal carbons, not in the middle of the molecule. Yes? Yes? This is your molecular formula and structural formula. Let's see the structural formula for this one. This will also be CH, Br, OH, and a CH3. Yes? Do you see molecular formula is the same? Structural formula is also the same, but they are still isomers of each other because of the arrangement. Here, the OH is to the right. Here, the OH is to the left. Here, the Br is to the left. Here, the Br is to the right. Is this clear? Now, one of them is called a D isomer or a positive isomer, and the other one is called a L isomer or a negative isomer. Now, which one is D, which one is L, you don't have to identify. You just need to make the mirror images, that's it. In cis trans, you had to identify the cis and trans. Here, you don't need to identify, neither do you have to name it. You don't have to call them D, L, positive, negative, no. I'm just telling you that one of the isomer is D, one is called L, one is called positive, one is called negative. Which is positive, which is negative, you don't need to know. Why do we call them positive and negative? Because one of these two will be a useful isomer, one may be a useless or a harmful isomer, right? So that's why we call these what? Positive and negative, or D and L, because I will just explain why. So one is called a D isomer. So one is a D isomer. So they can be, one is a D or L isomer, or you can call them a positive and a negative isomer. You don't have to identify them. You only need to draw them. Clear? Is this clear? Now, why do we call them positive, negative? I told you because one is a useful isomer, one is a useless or a harmful isomer. So one of the isomer so the useful one is called positive, and one of them is a harmful or a useless isomer, and we call that what? Negative isomer. Yes? Now, these isomers, if you see, the cis and trans, if you remember, had different boiling points. Cis had a higher, trans had a lower boiling point. Let's see here. So here, if I make dipoles, where will my dipoles lie? Towards the Br and towards the OH. Towards the O, towards the Br. Do you see their polarity is kind of the same? Yes, the dipoles are in the same direction. Do you see that? Yes. So since their polarity is the same, the polarity of the optical isomers is the same. Therefore, they are what? Therefore, they have the same boiling point. Why will they have the same boiling point? Because their polarity is the same. Their intermolecular force strength would be the same. So how will we differentiate between them? So how do you differentiate between them? The optical isomers are differentiated. So the two optical isomers are differentiated on the basis of the effect on polarized light. One of the isomer rotates clockwise and one of the isomer rotates anti-clockwise in polarized light. So one isomer rotates clockwise and the other rotates anti-clockwise in polarized light. And that's how you differentiate between the two. That's why we call them D and L. One is dexorotatory, the other is levorotatory. You don't really need to know that, but just that they can be differentiated by their effect on polarized light. One will spin clockwise and one will spin anti-clockwise. Clear? Now, there are certain mixtures which consist of 50% of the D isomer and 50% of the L isomer. So some mixtures, there are some mixtures that contain 50% of the D isomer and 50% of the L isomer. Or can we say both the isomers are in what ratio? 1:1 ratio. Such mixtures are called racemic mixtures. What do we call such mixtures? Such mixtures are called racemic mixtures, where we have what? 50% of each isomer. Clear? Understood? Is this clear? All right. Now, if you have a compound which has more than one chiral carbon, each chiral carbon shows how many isomers? 2. Yeah? So if you have more than one chiral carbon, then how many total isomers will we have? So the total number of isomers would be 2 to the power n. What would it be? 2 to the power n, where n is the number of chiral centers or the chiral carbon. So if you have like 3 chiral carbons in a compound, how many total isomers will we have? 2 to the power 3. If you have 4 chiral carbons, the total number of isomers will be 2 to the power 4. And that also applies if you have more than one carbon-carbon double bond showing cis trans. If you have, let's say, more than one double bond in a compound and 2 or 3 of the double bonds, they show cis trans. They are capable of showing geometric. So how many total geometric isomers will you have? Again, 2 to the power n, where n will be the total number of carbon-carbon double bonds showing cis trans. Understood? Is this clear? So if you have more than one chiral center that can show optical isomers, is why it will be called chiral center. So if you have a chiral carbon more than one, then your total number of isomers will be 2 to the power n, where n is the number of chiral centers. Likewise, if you have more than one double bond, so if you have more than one double bond that is capable of showing geometric isomerism, so the total number of isomers would again be what? 2 to the power n, where n here is the number of double bonds that can show cis trans. Clear? Is this understood? Do you all get it? Now, let's see benzene and how we can identify a chiral center, if there is any, in a benzene ring. You don't need to know structure of benzene or anything. You just need to know how to identify chiral centers in benzene. Let's see. So let's see this. Benzene is this structure right here. This right here is benzene. So this right here is what? Benzene. It has 6 carbons and 6 hydrogens. Each corner here is a carbon, right? And each carbon is making 3 bonds. How? 1, 2, and this ring that you see in the middle, that is also a bond. All right, so each carbon is making 3 bonds. The 4th will be a hydrogen. So each carbon has 1 hydrogen. Yes? So you have C6H6. Now, if you look around this, none of these carbon in benzene ring are chiral. So you should know no chiral center or carbon in benzene. So you have no chiral center, no chiral carbon in benzene. Why am I telling you this? Because right here, why? Now you'll be like, Miss, why is there no chiral carbon? Because this right here, the ring that you see in the middle is a pi ring. So if you have pi bonds, can it be sp3 hybridized? No. These carbons are sp2 hybridized in benzene. All right. So none of these are chiral. Now, why am I telling you this? You'll be like, this is so complicated. How will you remember? You don't have to. You just need to ignore if you see something like this in your question. Asking you to count the number of chiral centers. If they ask you, if you see a cyclohexane like this with a ring in the middle, this is benzene. This will have no chiral centers. You just gotta ignore it. All right? Because they will give you big structures in your MCQs and ask you to calculate the number of chiral centers, right? So if you see this ring, benzene ring, you know that it has no chiral centers. Clear? So you can just ignore it, not waste your time trying to find out how many chiral centers does it have because it has none. Clear? All right. Now, let's see this. So let's see an example. CH, Cl, Br, CH3. Now, if they ask you to identify the chiral center and draw the optical isomers, how will we do this? So they usually give you the structural formula. They will not display it for you so that it's easy for you to identify the chiral. They will give you structural formula, and from this you will have to deduce the chiral center. Let's see. So this is CHCl, Br, CH3. So that means there is a carbon with a H, with a Cl, with a Br, with a CH3. Now you'll be like, Miss, is it important that we put it in this order? Can I not do this? Can we not put the CH3 here and the H here and the Cl here and the Br here? Like, is it important that we put it in the order that you told us? Is there an order that we have to specifically follow? No. You can put it anywhere, any of these in any order. And this becomes your first isomer. Once you've made your first isomer, the second has to be a mirror image of this. So you make the first one, put it in whichever order you want, right? Put the CH3 wherever, put the H wherever, put the Br wherever, and put the Cl wherever you want. Once you have made the first isomer, the other one has to be what? A mirror image. And how will you draw it? Now that you've drawn the first one, the other one will be a mirror image. And how will we show the mirror image? The H is to the right. So now we'll draw the H to the left. Clear? Br is to the left. We will now draw it to the right. And everything else will be the same. Clear? And this right here, these are your optical isomers or mirror images of each other. And this right here is the chiral center. You can mark the chiral center with an asterisk. Clear? All good? Any questions? Do you guys understand this? Kids online, do you get it?